Okay, everybody, this is chapter 2, section 1. In geometry, these next few chapters kind of roll together, and we're looking at rules of math. Math is a pretty black and white subject. There's no real gray area, kind of like our English classes where, English is a language, but it's got rules of how you're supposed to speak and put words together. But then we have all these gray areas where we kind of break the rules and we still use them. And you can't do that in math. So in these couple chapters, we're going to look at how to prove something's true or prove that something's false. And you kind of do that in your science classes with hypotheses, and conclusions. Okay. So anyway, starting with this, we're going to look at patterns first. So we've got these. In example A, we've got these series of blocks, and we're going to add blocks to the next set of blocks and try to predict what the next one would be. So they give us a series of 3 sets of blocks, and obviously I'm adding to it. I need to be able to predict what the 4th set of blocks might look like. Okay, so you're going to get something that's going to look like this. Okay, where I kind of added 1 to each part of that group of blocks from the 3rd one. Okay, in part B here, we're giving you a series of numbers, and we're going, progressing from one number to the next. Well, how are you doing that? Okay, so if I look at this, to go from 1 to 2, that's pretty obvious. I'm going to add 1. Okay, and go to 2 to 4, I added 2. And to 4 to 7 on 3, and 7 to 11 on adding 4. So what do you think I have to do to get to the next number? Well, I'm adding consecutive numbers. Okay, so when we're doing this stuff, we also have to explain how are we moving from one to the next. So you have to come up with the actual inductive reasoning of what the next number would be and how we actually did it. Okay, so the next number should be 16, and I had to, my next consecutive number would have been adding by 5. Okay, we're looking at C. Then I'm looking at geometric figures. And I start with a triangle, I go to a square, I go to a pentagon. So it looks to me like I'm adding sides to the previous figure. Okay, so I think I'm going to get a 6-sided hexagon next. Okay, so I think that's pretty straightforward, just predicting. You guys probably have done that in other math classes, so it shouldn't be too tough to understand. But then figuring out what the pattern is sometimes is going to be the harder part. So you look at D now. I got a series of numbers again. How am I progressing from one number to the next? Well, to go from 2 to 6, I think I would add 4. Okay. And if I added 4 to 6, I get 10, but my next number is actually 18. Well, I have to add 12 to get there. And then to go to 18 to 54 is something, and I can't get a real good reasoning from that. So I need to look at something else. Another way to go from 2 to 6 is to multiply by 3. And then to go from 6 to 18, I would again multiply by 3. So does that pattern continue on? Well, to get from 18 to 54, yes, I do multiply by 3. Okay, so there's my pattern. I'm multiplying by 3. So sometimes, you've got to try something that won't work. You got to just go try to figure something else out. So that if I keep multiplying by 3, my last number should be 162. Okay. All right. So hopefully that was pretty straightforward for you. If you'll write down this definition for a counterexample, this is going to be pretty important. We're going to use this for a while. So a counterexample is an example sorry about my writing, is an example that shows a conjecture is false. Okay, so like I said, we're going to use this a lot going forward, so it's important we have that. First off, let's talk about, well, what is a conjecture, okay? We could think of it as an educated guess, but a little more appropriate would be a hypothesis. Okay, and in science, you create a hypothesis. It's your educated guess that, hey, if this happens, then something's going to react, and this will happen. And then you would do an experiment and then prove it or disprove it, your hypothesis, and then you have to make a conclusion. So we're going to do stuff like that. Okay. So in this particular example here, we need to, for example, A, B, and C, we need to be able to prove that there's something that I can use to prove that this statement is actually false. Okay. So for all real numbers x, the expression x squared is greater than or equal to x. So I need to find something that I could say is x, but then I'm going to square it, and I have to disprove that whenever I square something, it's always going to be bigger than what I started with. Okay. So I'll give you a second to think about that. What kind of number, if I squared it, would not be greater than or equal to what I originally started with? Okay. They give me a little hint here. Okay. Fractions. Okay. So let's say x equals, and I'll just come up with a pretty easy fraction. Okay. X equals 1/2. Okay. But I'm now going to square it. Okay. And when I square that, I really get 1/2 times 1/2. Well, that equals 1/4. So is my x squared greater than or equal to what I started with? And it's not. 1/4 is smaller than 1/2. Okay, so that's a counterexample. We found something to disprove that statement that they gave me to start with. Okay, this also would work with decimals. Okay, if you had something like 0.5, let's say x equals 0.5. If x equals 0.5 and you squared it, okay, I would get 0.25. Right? So this is actually smaller than what I started with. Okay. Part B, for all real numbers x, the expression the square root of x is greater than 0. This one's kind of a tricky question. There's really only one answer for this. What some kids will say, well, how about -2? Well, you can't take the square root of a negative number. Okay, that goes against the rules of what a square root is. I need the same number times itself to get what's in there. And the only way I can get a negative number is a positive and a negative value. So that goes against the rule of a square root. So there's only really one answer. If I take the square root of 0, I get 0. And that's not greater than 0, it's equal to. So you kind of have to read the question there a little bit and be able to do that. Okay? All right, last one. If the product of two numbers is even, then the two numbers must have been even. Now remember, product is when I multiply two numbers together. That's the answer. So I need something to disprove that. Well, if they're telling me the two numbers must be even, then I need to figure out a way to get an even answer when I have a positive or odd number and an even number. Okay, lost my train of thought there. So one example might be something like 3 is odd times 4 is even, and that gets me an even answer. Okay, so they're saying it has to be, it's the only way I can get an even answer is if both of those had to be even numbers, and we just kind of disproved that. And then you could do a whole bunch of different examples, okay? And that's one thing about counterexamples is I only need one answer to disprove something, okay? Everybody good? All right. So I believe that was a little way to look at patterns. So we have just this really quick one. If I'm looking at this, I'm going to be squaring numbers. So x or 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. So the next one would be 4 squared is 16. So I'm squaring consecutive numbers. Okay. In this one, I look at my set of numbers, and it looks like I'm adding 0.5 to each number. So my next one would be 8.5. Okay. This one's a little bit different. You could probably come up with some different things, but it looks like I'm adding a place of 0 to the previous number. So I get something like that. In number 4, I look at my numbers and they're decreasing this time. So how am I just decreasing? Well, to go from 10 to 5, it looks like I would subtract 5. But to go from 5 to 2.5, I'm subtracting 2.5. So that's not a pattern. Okay. So we need to come up with something maybe a little bit different. Another way to go from 10 to 5 is to divide by 2. So maybe I went from 5 to 2.5 by dividing by 2, and I do. Okay, so if I divide 2.5 by 2, I'm going to get 1.25. Okay. Question number 5, a little bit different. So we're kind of increasing our abilities here. To go from 256 to 16, yikes, I'm not really sure about that. To go from 16 to 4, I'm not really sure about that either. And then I got to use some kind of pattern to go from 2 to the next number, okay? So this one's a little bit tough, but if I take the square root of 256, I get 16. And if I take the square root of 16, I get 4. And if I take the square root of that, I get 2. So if I take the square root of 2, I think I get like 1.4. I can't remember exactly what that is. I didn't look at my notes, but I think that's I might have rounded that one. Okay, so I'm taking the square root of the number previous. Okay. All right. This one's a little bit tougher. Okay, and we gave you kind of a clue here. Look at every other number on 6. So if I look here, every other number. Okay, what am I doing? Well, it looks like I'm adding 2. So I'm adding 2 to every other number. So if I add 2 to that, I should get 8. Okay. If I look here, every other number, I'm adding 1, adding 1, adding 1. Okay. So if that was 8, then I think the next number becomes 2. All right. Good there? Okay. So hopefully, deductive reasoning is something we're going to use a lot, but being able to use counterexamples is really what we got to be able to do. Okay. All right. Thanks.